For the module on measures of disease frequency, this is the last lecture segment, and this is the section on proportion surviving. So, in fact, for a very basic epidemiology course like this, or in a textbook chapter on basic measures of disease frequency, they usually will not talk about survival analysis or proportion surviving in a very introductory level view of the subject. However, for those, I know that many people participating in this Master's in Clinical Investigation and in this epidemiology course are clinicians, are reading the clinical research, and you will see over and over again in that literature this concept of proportion surviving and the use of survival analysis. And so I think that and it's considered a very more advanced subject because of the math potentially involved. And if you're really going to calculate this for a study, definitely work with a statistician. But in terms of reading the literature and understanding what you see when you see a survival analysis, I think that the concepts are straightforward enough that we should just give you a little introduction to it in this course. So this segment is going to be about proportion surviving. In the cancer epidemiology field, we often see estimates of the 5-year survival. The 5-year survival following the diagnosis of this stage of disease compared to the 5-year survival for that stage of disease. In other fields, they may talk about the 1-year survival or the 6-month survival or the 10-year survival. The principle is kind of the same, but what proportion are surviving at the end of a follow-up period? Or it might be not surviving just in terms of alive or dead, but what proportion are free of disease at the end of a follow-up period or are free of whatever disease event or state that we might be interested in. Usually in clinical study populations, we're still going to have the problem of patients who are censored and patients who do not have 5 years of follow-up. And in fact, in clinical studies, what we often have is people who have been enrolled onto the study at different time points. So someone was diagnosed with disease in 2016, someone else was diagnosed in 2013, someone else was diagnosed in 2017. We want to estimate the 5-year survival, but some of those people have not even been followed for 5 years yet. Do we just have to throw them out of our calculation? Don't give those data to the statistician because they haven't been around for 5 years yet. Actually, they can contribute information. So this whole concept of censored observations and people lost to follow-up also applies when we're thinking about survival. So throwing people out may potentially contribute bias. So in fact, if we use the same graphic that we talked about before, if we had a study population where everyone had complete follow-up to 5 years, the calculation of proportion surviving out of the original population at risk does again become a simple proportion. So here, if each horizontal line is the person who is surviving, who is a person who's being observed from time 0, and the line just ends this time. I don't have a filled circle at the end, but the line just ends when the person is no longer surviving. And then if people are gradually dying, then the total proportion surviving, which was 1 at the far left, is really just measured by the top of the graph, right? And it keeps dropping every time someone dies in the study. So the proportion surviving is literally just the top line there. And if we just mentally erase all the other horizontal lines, what we would have right there is our Kaplan-Meier curve. It's actually as simple as that in concept, the proportion surviving. So if we have complete follow-up, if we have a closed study population, our proportion surviving is how many are still surviving out of how many were in the population at risk at the beginning of the study. So in the closed cohort, the proportion surviving equals the number of individuals still at risk at the end of the interval divided by the number at risk of the beginning at the interval. It's also 1 minus the incidence proportion. So, and again, in a closed population, proportion surviving, incidence proportion surviving free of the event versus the incidence proportion. So in this case, if the event of interest is death, the proportion surviving free of death is equal to 1 minus the incidence proportion of death in the same population. So very straightforward concept. And again, going back, the proportion surviving, if we erase those horizontal lines, we would be actually drawing the Kaplan-Meier curve, which I know some of you are very familiar with and you've seen in a lot of articles. So if you have a closed population, you can just draw that little Kaplan-Meier curve with a pencil and a ruler based on your counts. Now getting just a tiny bit of math, if we divide the follow-up time into small intervals, it turns out that the product of the proportion surviving over each interval equals the proportion surviving calculated over the whole interval. So I'm going to arbitrarily draw 3 intervals here, time 1, time 2, and time 3. So the proportion surviving from time 0 to time 1, the denominator is 25. That's how many horizontal lines are there at time 0. And by time 1, 21 are surviving, so that proportion is 0.84. And then from time 1 to time 2, now the denominator is 21, because that's how many were surviving at time 1. And by the time we arrive at time 2, we've lost 2 more, so our proportion surviving for that time interval is 19 over 21, or 0.9. And for time 3, between times 2 and times 3, now we have 19 in the denominator. 19 entered that period of observation, and 17 were free of the event by the end of it, so 17 over 19 is 0.89. But if we ignored those smaller time intervals and just said, well, what about our whole time period? That would be from time 0, when we started with 25 people, to time 3, when we had 17 left free of the event of interest, so that's 0.68. So again, the interesting thing is that if we take the calculations of 0 to 1, 1 to 2, 2 to 3, and multiply them together, we actually get 0.68. This concept is very useful because when we talk about, so this is the closed population and this is the simple mathematical example, but when we talk about the dynamic population, suppose people are leaving this population without the event of interest, they're not dying, they just moved away or were lost to observation for the study. We can use this concept of the time intervals to calculate our proportion surviving, even in a dynamic population. So the approach is going to be to divide the time into intervals and include the censored individuals in the calculation for the intervals during which they were observed. So now I've got a new population here. So everyone enters at time 0. They're in the population at risk. And then I've brought back my blue closed circles for people who have the failure event or the event of interest for the study. But then we've got the open circles for those who are lost to observation without having the event. So we can calculate the proportion surviving from these data by using that same mathematical trick of dividing into intervals. So the number entering, this time instead of 25, for some reason it's 24. So the denominator for the first time period, 0 to 1, is 24. And then by time 1, there are 20 who are free of the disease event. So that proportion is 0.83. But then for the next time interval from 1 to 2, you have that 20 who are left, but 2 of them are lost to observation. So the new denominator is now 18. And by the end of that time interval, one of them has had the event, so free of the event is 17. And then entering the next time interval, we've lost more people from censoring. So the denominator keeps changing in addition to the numerator. But if we calculate a proportion for each of these time intervals, so for some reason I drew 6 time intervals this time, we get an overall proportion surviving at time 5 of 0.63. So even though some of the people entering that study did not have 5 years of observation, they did contribute data and they did have periods of time free of the event of interest. So we are going to use them to calculate those data. So again, this becomes very relevant when you are reading articles and they show you a survival plot and they say, oh yes, so we started accruing subjects for our study in 2012 and we're publishing this article in 2018 and here's the 5-year survival. But in fact, there's people who weren't even enrolled onto the study until 2015, 2016, 2017. Data from those subjects is still going into that analysis. They are not showing you this graphic in quite the same way, but they are doing an analysis that correctly accounts for the censoring of those people who have a shorter period of observation. It may not even exactly match this, but this concept of people being censored, lost to observation, and no longer contributing person time can be accounted for in those Kaplan-Meier curves. So for a survival analysis, every observation is going to have a value for 2 variables, time and what we call failure. So what's mathematically called or statistically called failure may actually not be a bad thing. It may be a good thing depending on how it's defined. But whatever the event of interest is, it may be the person is cured or the person becomes disease-free or whatever. But you need two variables to do a survival analysis. So time is the time at which they're no longer under observation, and failure is a general term for the outcome of interest: incident, disease, death, recovery, relapse. And usually coded 1 for fail and 0 for censored. So the slide that I showed you earlier with that, made up dynamic cohort of people entering the population at risk, then I made this little data set. And this, if you go back and forth between the two slides on your handout, I don't have them both next to each other on my slides, but these are the exact data. So observation number 1 at the top is the person who contributed observation time for between 0 and 1. So their time variable, their t, is 1. And then they did fail. They were a closed blue circle. Then the next person down, observation 2, person number 2, ID number 2, I also had 1 unit of time and was a failure. The same was true for 1 through 4. And then the 5th row of data, that person actually got out to time 2, but then was a failure. So their time is 2, their failure is fail. And so on. So we happen to organize them so that all the failures were at the top of the graphic. So 1 through 8 are all 1s in the failure column. So observation 9 was observed for the whole 6 units of time and then never had a failure. So that person's time variable is 6 and their failure variable is 0. And all the others, there are varying amounts of time under observation, but they ended in censoring, so they are all 0s on the failure variable. So just in terms of thinking about a survival analysis or how are they getting this Kaplan-Meier curve, there's a data set under there that has a time for everyone and a failure variable for everyone. And then I can actually set those up in statistical software in Stata and tell it that we have 24 observations and so on from those data in the previous slide. And then I can say, so what is Stata? Can you give me a list of the survival experience of that data set that I just gave you? And so it tells us the survival time at each interval, the cumulative survival at each interval, taking into account both the failures and the censoring, the net loss. And so then you can ask Stata to plot that data for you, and it will give you say SCS graph, and Stata will give you this little graphic. So that corresponds to the dynamic cohort that I had drawn in the slide earlier. So again, the point of going into this survival time, not something that you will be asked to calculate for yourself, not something that, we may give a try of running this in Stata. But the main point of introducing it right now is that I know that a lot of you are reading articles with this approach used, and just be aware that there is this issue of dynamic populations, but that they are taking it into account if they use the Kaplan-Meier approach. And so when you're collecting data for a study and you're thinking about people and disease events and failures over time, you need to keep track of the time under observation for everyone and the time that those events occur. So going back to the objective of this lecture, time is just a really critical variable in epidemiology. You've always got to be thinking about time. Okay, so just as a little bit of a summary, though, of the whole this whole concept of measures of disease frequency. This is from one of your optional readings from the Grimes and Schultz article series in The Lancet on epidemiology methods. So this figure is rates, proportions, ratios. What are these different measures? So is the numerator included in the denominator? So if the numerator is included in the denominator, then that makes it, if yes, that makes it a proportion. If no, that makes it a ratio. And this is another thing that a lot of people in their daily life don't think of that much about the difference between a proportion and a ratio. I think it's really only gambling and odds that's using a lot of ratios. The numerator is not included in the denominator. We'll get into those later in this course because we have odds ratios and some different ratios. But in terms of measures of disease frequency, the numerator is included in the denominator, and that makes it a proportion, and then is in time included in the denominator. So if time is in the denominator, it's a rate. If not, it's a proportion, which we might also call a risk.